first off, and I'm going to be laying some foundations, bringing together evidence accumulation models and models of reinforcement learning, which is our okay, and hopefully something will happen there. Yeah. Okay, so these foundations are going to be around these two papers. So particularly this, which will talk about a new way of thinking about evidence accumulation, that one that takes a step further and brings in the effects of time. All right, so about what essentially are very, very simple models, usually linear independent stationary races. And so the accumulation is linear, the accumulators are independent, the input signal is stationary. And that sort of model was first proposed by Vickers back in '79. And that's been around for quite a long time. And another one that you're probably more familiar with is something like the simple diffusion decision model or drift diffusion model, depending on how you like to call it, which adds some sort of feed-forward competition. And so you get representations, or you get accumulation like this with noisy paths towards one of two boundaries. This is a sort of representing the whole thing as a single system. So the trouble with this very simple version of the DDM, it's been known for many, many years just not to fit behavioural data at all. In particular, it doesn't get the speed of errors and corrects right. And you need some more complexity, like the idea of variability in parameters from trial to trial, or perhaps collapsing bounds. This very simple one is one that I'm going to focus on a bit. Has had a bit of a revival and interest recently. A paper by Tillman and Logan pointed out that in this model, where there is the diffusion processes, these wiggly lines, are completely independent of each other, and yet it does a fairly good job. But that kind of seems like it must be wrong in many ways, and surely that we can't have things that simple. Don't we need some sort of recurrent competition to make decisions? And so models like the leaky competitive accumulator of Usher and McClellan, and competitive interactions. And so if this is a trace of two accumulators, then you see as one goes up, it pushes the other one down. And an even more really plausible version by Wang here, which has some self-excitation and some other processes going on, an interneuron feeding that out. Isn't action selection even more complicated in the brain? So and this is quite an old circuit diagram of what may well be going on in order to make even quite simple perceptual decisions. So my question is, can this complexity be usefully approximated by something? People have conceptually thought about this. This is about sort of ideas that we can talk about a bias or a threshold and some sort of likelihood, but I'm going to go even simpler than that in many ways. So here's an overview of the talk. I just want to introduce recent developments in cognitive decision making. And then go on to an even grosser. Whoops, I think the second aim that I've got here is to introduce or set the stage for a way to integrate model-free reinforcement learning. Next talk by Stephen Militek and Russ Bogue. I'll first of all talk about an even grosser simplification, which removes the stochasticity, the advantage linear ballistic accumulator, or ALBA, and point out how you can get important concepts like urgency, competition, and magnitude effects in a very transparent way, and in that ALBA model. And how that model can also account for competitive effects, things like the near competitor effect. I'll define that in Hicks' law, which is the change in response time as you get more, you have to accumulate more and more. End up briefly talking about how to, in these sort of very simple model frameworks, bring in the time, bring sense of time in this model called the time racing diffusion model, which directly gives a role for time in decision making. It's this binary advantage LBA, so just for a binary case here, an LBA simplifies things even further. If we have decision time going this way and evidence going up this way, then this is an accumulation. It's just linear, okay? So no noise there. the noise system. So there's some random variation. These are two accumulators racing each other, and the rate of accumulation, and that varies from trial to trial. So effectively, this statement saying that perhaps variability from trial to trial dominates variability within trial, and we can trial variability is not there. The idea of an advantage accumulation is to say that this accumulator likes ones and this one likes twos, and so they accumulate the advantage of 1 over 2. So you've got two choices, it's binary, or 2 over 1. So say you've got stimulus 1 and stimulus 2. So you compare those two as input. However, that's not enough. You need another couple of terms to make this sort of a complete and effective model of specifying the drift rates. So these are equations for the drift rates. The drift rate for this accumulator, the 1, 2, has first of all an urgency term. This is a stimulus independent term, well, not completely independent, perhaps the trigger, and it's something that drives you to make a decision. So you've got some positive accumulation happening. And then the second thing that you need is X from the total strength of the stimulus inputs. I'll talk about stimulus here, and I'll use brightness as an example, and then we'll talk about value and total value. So if you're making decisions between things that are just work, then that has some effect on decisions, not entirely driven just by this difference term, which is what something does. It abstracts everything but the difference, although there are variants on that. So the idea is that we can talk about these things: urgency, magnitude, and the advantage. So that binary advantage, LBA, you could think of it in some diagrams, and the stimulus comes in here. We've got something that takes a sum and magnitude effect. We've got something that takes the difference here and then in both directions, and that feeds in the difference effect, and then we've got some sort of urgency term here. Typically, what you get when you fit such models is that decision making is mostly relative. It's mostly about difference, but partially absolute. There's something about the strength or the magnitude that matters there. And you could, if you want to rearrange that equation and think of it in terms of an excitatory term and an inhibitory term, where if you're accumulating ones, then it's going to have strong excitation from stimulus 1 and weaker inhibition from stimulus 2. Okay. Just as an aside here, I'm in the perspective of cognitive models that are fit to behavioural data, and one thing that's very important in doing so is to not just take account of accuracy and mean RT, but also look at the shape of response time distribution. So here's a histogram of the time to respond, and this is often abstracted away into a representation of the middle, the median, the 90th percentile, the sort of slow response, the fast responses. Here's a graph that might present that in that sort of format, so you can see the slow responses. Here are the fast ones, and here are the medium ones. We've got that for a set of 3 conditions there. Well, all of the I'm going to talk about are estimated with a differential evolution, Bayesian fitting, and so we'll often plot things and put around them 95% credible intervals. So that's our 95% credible interval, for example, for the slowest responses, that 90th percentile, as a function of something over here, which in this case was learning. So a little aside, to talk about this evidence of this partially absolute and most, I'm going to look at some fits to a study which looked at choice for which is the brightest or which has the most luminance. As a small aside here, these sort of tasks are quite good because there's been, I know that random dot motion tasks get used a lot, but they have a very big, there's been some recent evidence indicating that there's a very large conceptual integration component. So there's a bit of a mix up between decision integration and integration at that perceptual level, and that this makes this paper, you get into all sorts of trouble. All right, so in this experiment, what we're doing is comparing a baseline condition with these brightnesses 0.4 and 0.3 with 2 other ones that are more overall bigger in magnitude, adding something. This one adds or multiplying, and we're going to compare performance those three. Now, what you get here is, here's a plot of those RTs again. You're faster if the magnitude is higher. So for these two here, where there's you're faster, but this one has the same difference, okay, as that one. It has the same proportional difference times 1.5, but plus 0.15, and you can use that to pull apart. You actually see that accuracy worst in this additive one. And so accuracy is really in this brightness discrimination you start seeing is about that difference. And of course, that follows from Fechner's law. So you can, the brightness is the log of luminance. Luminance is the thing, brightness is the subjective thing. When you fit a model like this, you see that you've got a big urgency component. You've got also a quite large weight on the difference, but still some effect of the sum. And these are fits of that model. You can see that it describes that data quite well. You can extend this sort of model to look at or look at competition effects. So here's some further data where we have, here's the correct answer, 0.4, but we have 3 factors in an easy trial. Here they're all 0.2. In a hard trial, 2 of them are actually easier, but one is a near competitor. And when that happens, things slow down. This is a thing to do. You make more mistakes, and you can't explain this with any sort of feed-forward normalization, because notice that the distractors all add up to the same amount. So, or the whole thing adds up to the same amount. The way in which you can explain this, have competition yet still stay in this independent racing accumulator framework, is to have now for every advantage. So we've got, let's say, we'll use an example where you have 3 things, and so you've got an accumulator that likes 1s and compares them to 2s, likes 1s and compares them to 3s, etc. And you don't terminate when 1 of them finish, and 2 of them finish. So here you've effectively got some counter, and so you're only going to stop when 1 of these pairs where both of them have passed. And it turns out that will then give you the competitive effects, but you'll maintain this independent linear accumulation or completely mathematically tractable. Again, you could think of this as some sort of network here, where you're taking these sums and differences. But the key thing is now a stopping rule is this one which counts those. Here's fits of that model, and you can see that it picks up nicely the difficulty effect. This is accuracy here. Sorry, I'm missing an x-axis, and this is RT. So it's got the slowing and the more difficult. And again, fitting the entire distribution. Notice that greater skew there, greater gap there between the median and the 90th and those two. Don't have time to go into it, but this also explains Hicks law, which is the logarithmic increase in RT as the number of choice options increases, and we showed that up to 9 options. Hicks law can drop out a bit after that. What about collapsing bounds? This is something that people have thought in the last sort of 10 or 20 years is necessary. There've been claims that it's an optimal thing to collapse your bounds in environments where difficulty varies unpredictably. Actually, if you simulate realistic parameters, that effect is negligible. Here's a recent paper on it, but I think anyone who's ever sort of fit these models and then played with it will see it's a very broad flat minimum. So there's not a great deal of reason to do that. But it is the case that you sometimes get, under particular circumstances, these much more symmetric RT distributions than you normally see, and there seems to be some passage of time going on. Here are 2 experiments that look at that. And the idea of the TRDM, the time racing diffusion model, is that instead of effectively kind of sneaking in a sense of time by having bounds collapse at a certain rate, we know a lot about the way that people make time judgments. They in fact do it in a way that looks like one of those diffusion models. So lots of evidence about that. So the idea was to bring that directly into a model in which we now have not only the racing evidence process, so this likes one thing, this likes another, but we've also got a timer that runs. And if that timer wins, you guess. You can do that. We did that in the racing diffusion because we wanted to drop away all trial-to-trial variability, but you can do it in you can do it in the LBA, and it'll also work quite well. This models traditional speed accuracy trade-off paradigms very well. Here's a paradigm that Peter Forsman used, where you either ask people to go fast, or you ask them to be accurate. And that was usually thought to just be thresholds that did that, but that mediated that. But in fact, this timing mechanism has a big role and fits better than all of the competitor sort of models out there like the DDM. And it's not just in this example, that's random dot motion. Here's one for lexical decision. You can also look at time manipulations that are direct, such as explicit deadlines, or in, say, Reutemann and Chatelain's work, not giving a reward and it's withheld. And again, you're able to account for, so one model can account for all of these things better than the competitors that are out there. Can also, in this explicit deadline thing, account for the time to, or count, out of sample, account for the times that you miss the deadline. And you get a good account of RT distribution as well. I won't have time for that one. Final one with this model is that we were able to link together a timing task, in which this is Stephen Militek's work, in which people were measured on their timing ability and also in their choice ability, same people. And what we got was a strong, fairly strong correlation between your ability to time and effects in the decision process. Okay, to summarise. The ALBA is a linear independent stationary race model that deals with competition. It's analytically tractable for n-choice independent accumulation, can accommodate relative and absolute effects, competition, Hicks law, and all in a fairly transparent and easy to apply way. TRDM adds in this idea of a timer being part of things. Future research, I don't think anyone's yet looked into that I know of, but there's obviously quite a bit of evidence about timing circuits, and it'd be interesting to see the relationships between these. And I'll end up there and just say that up next, the next talk is going to talk about using this advantage framework to put it together with reinforcement learning. And unfortunately, I don't think there's room to put this in, but we've also extended it to put in the timer. Okay, thanks very much. And I will stop my sharing. I think I have a couple of minutes for questions. Let's start. Yeah, there we go. I'll just have a look in the Q&A. Yes, so, okay. There's one question in there that says, does the timing agreement act the same role as urgency? In the urgency gating model, no, it doesn't act in the same way or in the same way as collapsing bounds. It can be similar if you allow partial information. That is, when instead of just guessing when the timer wins, you look at the state of the other accumulators and you get something. That becomes more similar to at least a collapsing bounds model. But note that within that TRDM framework, you can think of it as like the ALBA, that you can also have a direct urgency term rather than something adding to the, well, acting in a different way, I guess, because urgency gating models have all been within that or largely been within that binary, you know, DDM type framework. Okay. And what have we got? We've got a minute, so I'll go with Johannes has a question about how is the advantage aspect, that is the X1 minus X2 and the X2 minus X1, more flexible than the DDM? So what's more flexible is not the advantage aspect, but rather the separating out the urgency and the magnitude term. In particular, the magnitude term is magnitude effects are hard for the DDM. Ratcliffe, Roger does have a paper where he shows that you can deal with them if you have the standard deviation of the trial-to-trial variable in drift rate go up proportional to the mean. And then, so essentially, I guess the bottom line of this is racing accumulators have obviously the ability to deal with magnitudes and differences. The DDM abstracts that away and so has to bring something else in, like trial-to-trial variability in rates, in order to get accuracy effects. I think we should stop there, and I think we're